Okay, for number 5, it says find the net area under the curve 2x plus 1 from a is equal to 0 to b is equal to 4. Part A wants us to approximate with two right rectangles. So the graph, let's figure out what our delta x is. That's going to be 4 minus 0 over 2 or 2. So it's going to be 0, 2, and 4. And it's going to look something like that. So the right rectangles hit here and here. And this would be up at 5, this would be up at 9. Again, if you plug in 2 and 4 into the function, that's how you get those. So my area here would be 2 times 5 plus 2 times 9, and that would be 28 as my approximation. So then for part B, they want us to do the same thing except for with 4 right rectangles. So my delta x is going to be 4 minus 0 over 4, which is equal to 1. And then if I draw my picture, 0, 1, 2, 3, and 4. And then if I do my right rectangles, and if I get the heights of each of these, this is 3, 5, 7, and 9. So to figure out my area, this would be 1 times 3 plus 5 plus 7 plus 9, which would get you 24. So 28, that's an estimate. 24 is a better estimate, like we were showing on the last section. The more rectangles we have, kind of the less like overcompensation that there is here, because they're smaller and smaller. And if we were to estimate this with 8, then it would be an even better estimation. So that kind of train of thought leads us to the definition of the definite integral. So if you check out the information on the worksheet about the definition of the definite integral, it talks about how we want more and more rectangles, so 100 rectangles, 1,000 rectangles, which leads us to using limits and having an infinite number of rectangles. So the formula for the definition of the definite integral is using a summation, because we're adding up an infinite amount of rectangles. And then if you look at the kind of the proof idea, it talks about what part of the formula is the height of the rectangles, which part of the formula is the width of the rectangles, and then we're adding them up. So let's look at doing that. So this would be part C. So I need to know what my delta x is, and that's going to be 4 minus 0 over n. So that's going to be 4 over n. I'm going to circle that just so I can refer back to it. X of k, that is going to be equal to 0 plus 4 over n times k. And that's equal to 4 over n k. Okay, so I want to, again, I'm referring to this formula for the definition of the definite integral. So this is going to be the limit as n approaches infinity. And this is from k goes from 1 to n. And I have the function, which is 2x plus 1, but I'm plugging in my x of k value. So it's going to be 2 times, instead of x, 4 over n k plus 1 times 4 over n. So this would be the this is going to be excuse me, this is going to be your height, and this is going to be your width. And what this means is that you're adding up an infinite amount of these rectangles. So it's going to actually get you the exact area under a curve. It's not going to be an approximation, it's going to be exact. So it's kind of a powerful concept here. Okay, so I have a lot of work to do with these series, which is why we have to do why we practice the series on the previous worksheet. So let's do some simplifying first. So the limit and that's going to be 8 over n k plus 1 times 4 over n. Let's distribute that 4 over n. Okay, then I want to split up the series. My next step is I actually want to pull out of the series any non-k values. So I want to pull out non-k values. So that 32 over n squared, I want to take that out. And the 4 over n, I want to take that out. So the limit is still there. Now when I take this 4 over n out, it leaves me with a 1 there because I don't have anything else left in there. So now I want to use my sigma formulas. And again, we were practicing that on the last worksheet. So the 32 over n squared, that was there because it was from before we pulled that out. The actual series part here, that's going to become n times n plus 1 over 2 plus 4 over n times, and then this 1 is going to become n. So let's do a lot of our simplifying. This is going to be the limit as n goes to infinity. And this is going to be of, well, one of the n's is going to cancel out here, and the 2 with 32 is going to be 16 times n plus 1 all over n plus 4, because those n's cancel out. And then this is going to be the limit as n goes to infinity. And I'm going to distribute the 16 here. So that'll be 16n plus 16 over n plus 4. And I'm running out of space. So let's go back to the previous slide. I forgot to give myself 3 different slides on this one. I only gave myself 2. There we go. So again, we had the 16n plus 16 over n plus 4. So let's actually split up that fraction. And this will be the limit as n goes to infinity. 16n over n plus 16 over n plus 4. So those n's will cancel out on the first fraction, and that'll leave me with 16 plus 16 over n plus 4. And then finally, I want to actually use the limit, because again, I'm going from, or as n goes to infinity, I want an infinite amount of rectangles. So this will be 16 plus 0, because anything over infinity, or 16 over infinity, is 0. Plus 4, and this is equal to 20. So this is an exact area. This is not an approximation. So we approximated it with 28 and 24, but the exact area is actually 20. So definitely a lot of steps on this with the series notation, series formulas. Definitely a lot of work.